And thank you all, and we had some very valuable discussion and for the previous talk. And probably you know this is the last talk for the morning section, and this is the only obstacle between you and your lunch. So I promise you I will make that as brief as possible. Thank you. So in this presentation, I will just discuss how to implement the wave propagation component. Is the second component for the Stolt remigration for the heterogeneous medium, and keep the equally effective for all frequencies property. So we're still in this section on the tree. As we have already discussed in previous presentations, we have already covered the image principle and for the Stolt C3 and to show that it's equally effective for all frequencies in previous presentation. This one, we will discuss how to implement the second one, a wave propagation model for heterogeneous and keep the equally effective for all frequencies property. So in previous tests we have shown the homogeneous median and the analytic G0DN is used for the Stolt C3 migration. Because the analytic G0DN, there is no any high frequency approximation or any compromise. So that is equally effective for all frequencies, is guaranteed. But our goal, our final goal, is to implement the equally effective for all frequencies wave propagation model for the C3 for heterogeneous medium. However, there is no analytical form for the G0DN for general heterogeneous medium. So we need a scheme to calculate the G0DN in heterogeneous medium numerically. That is why we propose the numerical scheme to calculate G0DN in heterogeneous medium. And the scheme is based on the theory expansion method, and the detail can be found in our report. As I promised, I didn't put the whole math detail derivation here to make the talk brief. But one thing I want to mention is there are two important parameters for the theory expansion approximation. One is step length, and one is number of terms. Our goal is to apply this numerical scheme on the heterogeneous case. But before we perform our numerical scheme on the heterogeneous case, we need to confirm the scheme can obtain sufficient accuracy so that we have enough confidence when we deal with the heterogeneous case to keep the effective for all frequencies property. How can we do that? The easiest way is that we compare the image by the numerical G0DN with a known equally effective for all frequency image result by the analytic G0DN. And then because the image for the same model with the same data will be unique, so if the two results match, we know that the numerical scheme is accurate enough. The problem is that the analytic G0DN, as we mentioned, can only be calculated in homogeneous medium. So that is why for the first half of this presentation, let's stay in the homogeneous world, not to go to heterogeneous yet, and to test the numerical scheme in the homogeneous. So next, I will show the example, a numerical example, and this numerical scheme on the homogeneous case to confirm the scheme can achieve sufficient accuracy compared to the analytical solution. Of course, if the parameters are chosen properly. The example, another meaning of this example is can provide a practical guide how to choose the proper parameters, the step length and the number of terms to achieve enough accuracy. So for the homogeneous example, we use the same very simple model, the C0 over C1 homogeneous background. And we use the same spectrum, the broadband data and the conventional data. And we have already seen this is the analytic C3 image result for the broadband data and the conventional data. And we know they are equally effective for all frequencies. So this is our target, is the benchmark. Now let's compare the numerical result with this analytical result. Because we want to do the comparison very detailed, so we zoom in this area, just in this area. Here is the zoom in section for the analytical result, analytic C3 result for the broadband data and conventional data. The blue lines here. Here is the numerical result from insufficient parameters. This result we intentionally use the insufficient parameter, which is not enough number of terms. we want to show you that if we use a bad parameter, we can get a bad result. And if we compare the numerical result, the red one, and the numerical analytical result, blue one, we see a huge difference, especially near the reflector. And if we use sufficient parameters, we use good parameters, we can get the numerical result really close to the analytical result, almost identical. So in each section, we should have two curves, the blue one and the red one, because they are almost identical. You cannot see two, they just overlay each other. And we mentioned that we need a good parameter of how good is good. So we do a lot of analysis on how to choose the parameter properly. Here is one table we showed for the image result that we keep a given step length and keep a given relative error tolerance, which is 1%, which will be the necessary number of terms to be used to achieve the good accuracy. And we have this here, the table is for the final image. We have that the similar table for each component, each frequent component for the G0DN. For the similar analysis, but for brief reason, we do not put all the tables here, and you can refer to the report. Several comments we want to make about the numbers. We know that our final target, final goal for the numerical scheme is a heterogeneous medium, and here we do the analysis on the homogeneous situation. And if we use the heterogeneous case, if we keep the same step length and the same error tolerance, the number of terms need to be larger. But still, the values for the from the tables can serve as an initial guide how to choose the parameter to achieve the enough accuracy for G0DN numerically for the heterogeneous case. Now let's step one step further to the heterogeneous case. As I have mentioned, in the homogeneous case, we have analytical result for G0DN, and we have known equally effective image result for the reflector. So we are confident that the numerical result is also equally effective for all frequencies. How about we have heterogeneity in the model? Now there is no analytical G0DN, there is no analytical image result. So how can we confirm our result, image result, and the wave propagation model is still equally effective for all frequencies in this heterogeneous case? Here is the way we can have confidence with that. We just put a one reflector below the heterogeneity. It's the C0 over C1 reflector, just below the heterogeneity. Then we use the numerical scheme and to perform the Stolt C3 migration to get the image for this reflector, the C0 C1 single reflector. Because the unique interpretability, we have the physical meaning for physical interpretation for this image, for C3. The image is that at each image point, we are predicting physical experiment at this local position with a small but positive time. For a small and positive time, the physical experiment will only care about the local properties, will not care about the properties far from them away. So for the image of this reflector, if you have the heterogeneity or not far from the reflector, does not matter. We will get the same image for the reflector for both models, the homogeneity or heterogeneity. So we know for the homogeneity model, we can get the imaging for this reflector by the analytical G0DN, and the result will be equally effective for all frequencies. And we know that the same image for the same reflector will be unique if we can match the numerical image result from the heterogeneous case with this analytical result from the homogeneous case. We are confident that the result is equally effective for all frequencies. So that is what I'm talking about. And for the homogeneous case, we have a no equally effective for all frequencies imaging result. And if we can compare the numerical result from the heterogeneous case with this, we are confident our implementation is perfect. For the future plan, the next step, First, we will reduce the computational cost by optimizing the trade-off between the two parameters, step length and the number of terms, to reduce the computation cost. That means that, for example, if we use the smaller step length, we can use the smaller number of terms. That will reduce computation cost. But we need to use more steps. That will increase the computation cost. So we need to balance those two parameters to get a minimum cost scheme for the numerical scheme. Second, we will test the numerical scheme for J0DN on heterogeneous synthetic model. And then we will seek the field data to test the numerical scheme J0DN for the Stolt C3 migration on field data. Finally, let's draw the conclusion. We proposed a numerical scheme to calculate the J0DN for heterogeneous medium, and we show the numerical scheme can achieve sufficient accuracy compared with the analytic solution in the homogeneous medium. We also provide a practical example for the parameters, the step length, and the number of terms for the numerical scheme to achieve good enough accuracy for homogeneous case. And even for heterogeneous, the value of this, the result for this analysis is still valuable. I serve as an initial guide. Finally, we show how to confirm the wave propagation model for C3 image is equally effective for all frequencies for the heterogeneous medium. We show the scheme. And that's all. Thank you.